To solve a system of inequalities by graphing, we're going to graph each of the inequalities and shade separately, and then see where the shading overlaps for each one. To start with the line x is greater than or equal to 0, we need to graph the line x equals 0. The line x equals 0 means that the x number always has to be 0. So we could have 0, 1, 0, 4, 0, 3, any of those numbers we want. X equals 0 is going to be a vertical line. As I'm making my line, I'm making it a solid line because it does say or equal to. If it was strictly greater than, I would use a dotted line. Then I need to decide which way to shade for that line. Typically we pick a point like 0, 0, but when 0, 0 is on the line, we need to pick another point, like maybe this point right here, 1, 9. If I plug in 1 for x and 9 for y, well, there isn't a place to put in the 9, but I get 1 is greater than or equal to 0. That's true, so I want to shade towards 1, 9, or on the right side of that line. The second line is a y equals line. That's going to be a horizontal line right at 0. It's a solid line again because it does say or equal to. And we're going to shade numbers that are greater than or equal to 0, so those numbers will be above this line. So far, the shading for this graph is overlapping in the first quadrant. We're shading things that are to the right of the red line and above the blue line. Now we need to graph the third line. We have a couple choices. We can either solve it for y and graph it using y equals mx plus b, or we can use the cover-up method and figure out that the y-intercept is 4. And if we cover up the y's, we can figure out that the x-intercept is 2. So if I go to the y-axis and make a y-intercept at 4, and on the x-axis make an x-intercept of 2, I can graph my line that way. The pattern looks like down 4 over 2, so if I keep going down 4 over 2, I'll get all of the nice points on this graph. You could also reduce 4 over 2 and make it 2 over 1. That'll work also. Either way, use something very straight and make a nice straight line connecting those 2 points. And then we need to decide which way to shade. So I'm going to plug in the point 0, 0 because 0, 0 is not on that blue line. If I put 0 in for x and 0 in for y, I get something that is true. So I want to shade towards 0, 0. The shading for those 3 lines overlap to make a small triangle. The second part of this question says, then name the coordinates of the vertices of the boundary. So the vertices are like the corners of this boundary, and there are 3 of them since it's a triangle. The vertices are at the point 0, 0, 2, 0, and 0, 4. We can use something like this in story problems to help us maximize or minimize a function. Typically, we're maximizing or minimizing a product function, and we have 2 variables that are both earning profit for us in the types of problems you will see. For things like that, we will have a function in 2 variables. It will have an x variable and a y variable. So one example of that sort of function might be f of xy equals 3x plus 2y minus 15. So if we wanted to figure out what's the value when x is 3 and y is negative 2, we just plug in 3 everywhere we see x and negative 2 everywhere we see y to get an answer. In this case, we get 9 minus 5 minus 15, or negative 10 for a value. Now, if we have a function that's bounded on some convex polynomial, so polynomial, remember, is just a shape. It has no curves, no gaps, or no overlaps. Convex means it doesn't cave in on itself. This would be concave. Convex is more of your typical sort of shape that does not have any indents on it, or none of the diagonals are outside of the shape. Now, if a function is bounded on some convex polynomial, there are infinitely many inputs for x and y. To find the maximum and the minimum of the function, we're going to use the vertex theorem. What that means is if I go back to the graph that we just had, there are infinitely many x and y numbers that I could plug in. I could plug in any of the points that are in there. So it looks like 1, 1 is in. I could plug that in for x and y. 0.5, 1 is also in there. 0.5, 2 is in the set. There are infinitely many things that I could plug in, and I don't want to plug all of them in to figure out where the maximum and the minimum are. So I'm going to use the vertex theorem. The vertex theorem says that the maximum and the minimum is only going to occur at a vertex of the boundary, one of those corners of the shape. So if we think back to that last graph, we had the little triangle for our boundary. We do not need to plug in all of the points that are in the middle to find the max and the min. We only need to look at the 3 corners, because this theorem says that the maximum and the minimum of that function are always going to occur at one of these vertices. Let's look at an example and try to find the maximum and minimum values for that function determined by those 4 inequalities. The first thing we need to do is graph all 4 and figure out what our shape is going to look like. I'm going to graph it using, I'm going to graph the first one using the cover-up method, and I'm going to see that the y-intercept is 3. And if I cover up the y's, I see that the x-intercept is 12. I'll use a solid line to connect it because, again, it does say or equal to. So there's my first line. Need to figure out which way to shade on that line. So I can plug in 0, 0 and see if that makes something that's true or not. If I plug in 0, 0, I get 0 plus 0 is less than or equal to 12. And that is true. So we're going to shade below this line or towards 0, 0. Pause the video and see if you can graph the other 3 lines on your own, and then we'll compare answers. When you graph all of the lines, the shading should all overlap in the middle of the graph and make a 4-sided shape or a quadrilateral. If you want to check your work on the graphs, you can look at the work that I showed. I want to point out that on the 4th graph, when I tried to do the x-intercepts and y-intercepts, they weren't very nice points, especially for the x-intercept. So instead of approximating, I decided to solve the equation for y and graph it in y equals mx plus b form. That was a little bit easier in that case. Also, if you look at my graphs, you'll notice that on each line I made all of the nice points. Doing that makes it easier to find out where the lines intersect. If you're just sketching the lines like you're doing a couple of points and then connecting them, sometimes it's more difficult to figure out where the lines intersect. And if you can't figure out where the lines intersect, what you're going to need to do is go back and solve the system of equations. Because remember, if you solve by substitution or elimination, what you're really doing is figuring out where 2 lines intersect. Now that's a lot more work than making a very clean and accurate graph. So I really recommend you make your graphs look very nice. Now that's just the first step in solving this problem. We've graphed it. We were supposed to figure out what are the maximum and minimum values for that f of x function. The vertex theorem tells us that the max and the min are going to happen at one of these 4 vertices. So it might happen at the point 2, -4. It might happen at 4, 2. It might happen at 0, 3, or at -2, 0. But we don't have to check any of the points in the middle. Any of these infinitely many points here in the middle, yes, they are solutions to all 4 equations. If I plugged them in, I would get true inequalities for all 4, but none of those are going to be maximums or minimums for the f of xy equation that we got. So now we're going to plug it in. The f of xy equation, if we plug in 4, 2, we're going to get 4 minus 2 plus 2, which equals 4, and do that for all of the vertices. So now we'll do f of 0, 3, f of -2, 0, and f of 2, -4. Alright, according to the vertex theorem, one of these will be the maximum, and it looks like the maximum is 2, -4, or it occurs at 2, -4. The maximum value is 8. And the minimum occurs at 0, 3, and the minimum value is -1. What this will mean in terms of a story problem is maybe x represents the number of bikes that you make, and y represents the number of cars that you make. If you're making 0 bikes and 3 cars, your profit is going to be -$1, and you're going to lose money in that situation. Now, this wasn't a story problem, and that's really not making a whole lot of sense, but in the story problems, we'll get lots of positive values, and we'll probably have a positive profit. Not always, but probably. Now, it really falls apart when we look at this one. If I make 2 bikes and I somehow create -4 cars, which really doesn't make sense, the profit would be $8. As we go into the next section, we'll do story problems, and then we'll talk more about what these points represent in terms of the problem. The other thing to point out about these is sometimes you will get situations where you have alternate optimal solutions, which means there's more than one point that produces the optimum value. Maybe when I plugged in 2, -4, I got 8. And maybe for some different problem, if I plugged in a different ordered pair, I would get the exact same maximum again. So there would be 2 alternatives for how you could optimize the situation. We'll talk more about that in the next section.